Morning, everybody. Welcome back to our refractory seminar online. We are starting the day with the topic of BOF converter, and for that topic we have two presenters. One is representing the application side. It's Jochen Schlüter. He's now as vice president with SMS, and he has been many years in his career production manager for BOF units, so a rich experience in that field. And the second presenter, who will join later through MS Teams connections into that presentation, is Michael Berger from RHI Magnesita, and he's representing the refractory side of that business. And with that, I would leave it to you and put you on stage.
Okay, Anders, thank you very much. Good morning, ladies and gentlemen. I will start immediately with my presentation due to the short time we have. At first, I would, after a short, brief introduction, I will talk a little bit about the blowing process, about charge materials, process sequences, and so on. And later on, we switch then a little bit more in the detail to the refractory part of this presentation. Yeah, I think you know this slide very much. The steel production worldwide is increasingly dramatically since the beginning of the middle of the 80s. This process is mainly driven through the steel production in China. China produces now around about the half of the worldwide steel production. But what you see here is only the annual steel production, and is not the capacity. And for me, it is at every time important to explain that there is a slight difference in the total installed capacity and in the worldwide steel production. So that means the capacity is much higher than the annual steel production. We produce now around about 1.9 billion ton of crude steel worldwide. On the next slide, you will see the following. I think don't read all the numbers and figures here on this sheet. I think important is the point that round about 2/3 of the steel production is produced in a BOF converter, and round about 1/3 is produced in electric arc furnaces. And this is important to know because the main steel production at the moment is the conventional route via blast furnaces through the converter in the secondary metallurgy. But I think one thing is important. When you look here, for example, the European unit, that means around about 60% of the steel production is produced in BOF shops and around about 40% in electric arc furnaces. But when you look a little bit more in detail, it's depending on the country and the countryside and location for the steel production. And when you look here, for example, in the Czech or the Slovak Republic, here's a huge amount of BOF steel production and a very small amount of electric arc furnaces. And when you look here, for example, in Greece, it is the opposite. So that means it's depending on the situation you have in the country, in the different countries, and it's the same in the rest of the world. Maybe in the near future, I think there will be a dramatically change in this way of steel production due to the CO2 debate we have at the moment worldwide to reduce the CO2 emissions, because the biggest emitter of CO2 is the blast furnace. And so a lot of discussions at the moment is to change the route with a direct reduction shaft and behind the direct reduction shaft to run an electric arc furnace. We will see what happens in a couple of years, but at the moment there's a big movement. Now we come a little bit more in detail to the basic oxygen furnace. What are the core components of an oxygen converter? In the middle, and the important point is that you have a steel vessel. This steel vessel is relined with refractory material where you put the hot metal and scrap in, and where you start your blowing process. This vessel has a top cone, a cylindrical part, and a bottom cone. Then it is fixed in a so-called trunnion ring. We have a big gear, a tilting drive that you can rotate the converter. This is important for the charging procedure and later on when you tap the steel out of the converter. You have here, to close the converter, you have here a bottom. So we have two different ways of a bottom. That means sometimes you have a replaceable bottom. That means for the relining purpose, you remove the bottom plate from the vessel, and then you can dismantle the refractory material inside the converter, and later on you can put a lift from the bottom into the converter, and then you bring all the bricks and all the refractory material for the relining inside the converter. Other converters, they have a complete vessel without a replaceable bottom. Then it means that you have put all your refractory material from the top into the converter for the relining purpose. The bottom is equipped with steering plugs, so that you can steer during the blowing process. Normally you use nitrogen, and in case that you have steel grades with a very low amount of nitrogen in the analysis, you can use argon. Later on I will explain why it is so important. Then the big importance point here, this is the oxygen lens. That means you drive the oxygen lens inside the converter, and then you blow the pure oxygen with a certain distance from the lens tip to the surface of the metal bars on the metal bars, and you try to penetrate one part of the oxygen inside the melt. To collect all the fumes coming out of the converter and the gases, and this is mainly CO and CO2. You have a gas cooler above the converter. You have a filter system behind that you can clean all the gases, because you have a lot of dust in your converter gas, so that you can achieve the requirements from the environmental side. Then you have here a kind of a ventilator to suck the gases out of the converter. And at least you have on top of the converter a bunker system. There you can put all your additives in a kind of a bunker system, so that you can feed this material during the blowing process, especially at the beginning of the blowing process, online or directly in your converter, and to support the activities and things inside the BF vessel. One important point is the lens, and that means it's the lens tip. You have a water-cooled lens, and at the tip of the lens you have a copper lens tip. Why is it copper? Because you need a high heat transfer, because the lens is inside in the converter with a very high temperature atmosphere, and you have to cool the lens to avoid that the lens will be destroyed. And one very important thing is the nozzle. And now the following is, the nozzle is built as a convergent cylindrical part and a divergent part of the nozzle. And this is important to know, because when you, in the center here of the lens, when you come with the oxygen from your oxygen supply and you blow it through the nozzle, then you have in the cylindrical part, and it is a kind of a throat, you have here a velocity of max 1 Mach. That means ultrasonic speed of 1 Mach. And due to the fact, and this was found out by Mr. Laval, when you enlarge the area behind this cylindrical part, in this divergent part of the nozzle, you enlarge the velocity. And this is important to know, because when the oxygen leaves the lens tip, then you have a velocity of 2 to 3 Mach. That means you double or third the velocity of the oxygen stream coming out of the lens tip. And this is important for the process, because then you have a very high impact of the oxygen stream on the surface of the metal bars, and some part of the oxygen can penetrate the metal bars and can do the chemical reactions inside the bars. So everything is water cooled to avoid any damage of the lens tip. You have in the inner part, you have the water cooling coming in, and then on the outer side, the water is going up to the top of the lens to the water cooling area where you recool the water. Very often the lenses have different number of nozzles, and this is depending on the size of the converter. That means of the tapping weight and of the dimension of the vessel. And but in the normal, in most cases, you have 5-hole lenses or 6-hole lenses where you blow your oxygen on the surface of the converter. The angle of the nozzles is different too. So that means they are not straight on the surface. All the tips have a special or certain angle that you can cover a bigger area on the surface of your converter when you blow the oxygen on the surface of the metal bars to penetrate it inside the bars. The most lens tips has an angle of 17.5 degree. Some cases, for example, at HKM, there's a lens tip is 23 degree. This is really unusual, and this depends on the geometry. That means the diameter and the height of your converter vessel, and you have to find out what the best type of lens tip is to avoid any sticking of slag and sculls on your lens. Only a few words to charge material. When you look here, at first you charge a scrap into your converter vessel. Later on, when scrap is in, you move the converter, in this case, in the other charging position, and you fill in the hot metal. This is important because at first you have to charge the scrap inside the converter, because very often, especially in winter time, you have some humidity, some water in the scrap, some ice or snow. And if you would do it in the opposite way, then the risk is very high that you get an explosive evaporation of water, and the scrap is thrown out of the converter, and it is from the safety side really critical. So that means at first you add scrap, and later on then hot metal. Here is a picture of a converter where the hot metal is filled in. So what are the additions and additives you add into the converter? And at first, very important is that you have here all the slag formers where you put it in the converter. That means the main portion is lime, or sometimes dolomite lime or MgO carriers. This is very important because you need the slag formers, because all the oxides you produce during your blowing process must be catched and binded in the slag. And for this, lime is absolutely necessary, that you can collect all the oxides coming out of your blowing process. Then you can add coolants in the BOF process about the bunker system. That means for coolant ore or pellets are very good because they have a high cooling efficiency, because the reduction of the ore is an endothermic reaction. That means it needs energy and cool your process down. Or you can use dust briquettes or cooling scrap. It's depending on the situation and on the cost price basis for the process. Sometimes you need some heating agents that you can correct the temperature. Very often coke is used. That means you bring artificial coke inside the process, and this coke is burned with the oxygen, and this is an exothermic reaction. That means you get a lot of energy from the combustion of coke. Yeah, let us talk about the process sequence and the place of reactions. What are the main tasks of the BOF process? I think the main task of the BOF process is the reduction of the following elements. At first, of carbon. Yeah, because you know that. Sorry, that was wrong. You know Okay. At first, you have to reduce carbon. Carbon is coming from the blast furnace, from the reduction process inside the blast furnace. And the hot metal is, depending on the temperature, saturated on carbon. That means you have to bring out the carbon, and the carbon value is around about 4.5% inside the hot metal. And so that means you have to oxidize the carbon. The second important point is that you have to reduce the phosphorus, because phosphorus is not useful for material properties later on when you have your finished products. It is not a well-known element, so that means you have to reduce phosphorus in the BOF converter. And the problem of the phos is that you can only reduce it in the BOF process, because you need an oxidation atmosphere for the dephosphorization. And later, after the tap of the BOF, there is no possibility to reduce phosphorus out of the liquid steel. Silicon and manganese will be reduced too. And this is the one aim of the BOF process, the reduction of the element. The second aim is to achieve the right tapping temperature, because you have to put all the necessary temperature here inside your metal bars. That means you need a temperature buffer for the alloying. All the treatment steps behind the BOF need a certain temperature, because there is a temperature consumption. Yeah, when you add alloys in your liquid metal bars, then you are losing temperature. You need temperature for all the process steps in the secondary metallurgy. For example, when you have a vacuum treatment behind, it is temperature consuming. So that means you have to put all the additions for all the treatment steps behind the BOF process in the tapping temperature of the BOF. But today, very often, and this is completely a change in the philosophy, you will have ladle furnaces behind the converter. So that means you can lower your tapping temperature and you can increase the temperature again, because you put the ladle in a ladle furnace for reheating of the melt.